The 5th annual Mork Family Department Student Research Symposium. So today is all about our students and all the great research that they're doing. It's basically the department's way to say thanks to the grad students and the undergrad students that are doing research. And I know what you're saying. This is a weird way to say thanks, to ask us to give presentations. But we like to see what the department overall is engaged in research-wise. We think it's a very nice activity for the students to see it, for the faculty to see it, and for our external judges to see it. And so we're running a little behind, so I think we'll go ahead and get started. So Thomas, our first talk will be by Thomas Valdez. You want to go ahead and load up your presentation. And Thomas is going to talk about some proton exchange membranes.
Actually, oxygen evolution on using proton exchange membranes for electrolysis. This will just take me a second. Can everybody hear me okay? Perfect. Thanks, Professor Lee. I'm going to move this just a little bit. Oh, there we go. It's a little I just wanted to thank everybody for being here for my presentation. I know it's the first one. It's very tough to get here at 10 a.m. I also want to thank the committee for selecting my abstract as a presentation. What I want to be talking to you about is what I've been doing research for about the last 2 years on, and it's essentially developing materials for oxygen evolution. And these are very special because they're meant to go into something that's called a water electrolyzer. And without further ado, we'll go ahead and go over the presentation outline. We're going to talk about a little bit about the motivation. The motivation behind all my work is essentially to try to develop a non-carbon-based energy carrier, say something like hydrogen, where you could actually use it to fuel something, to transport some power. So we're looking at hydrogen in this case as an energy carrier. We're going to go a little bit about the research background, what actually sparked our interest in actually doing this work. We're going to talk about materials development, so we're going to see some processes that I use to actually fabricate our catalyst. Then we're going to take that catalyst and we're going to try to understand it using some standard material science techniques, looking at X-ray diffraction and whatnot. Then finally, we're going to do what my heart is in, and that's a lot of electrochemistry. So I have a couple of different electrochemical techniques that some people may not be interested in, so I'm going to try to introduce them and kind of go over the different aspects and what they do and why are they so important for us actually doing these materials. And finally, I actually threw this chart, and hopefully I could actually get to this. We took these materials that we discovered, or that we developed, I should say, and we actually applied them to a working system. And you're going to get to see a couple of charts where you're going to say, oh, okay, wow, this material really made an impact. So what I really want you to get when you're listening to my presentation here is I want you to see how some real basic research has such a huge impact and say something that's, how can you say, industrially viable. So moving on, we have this concept of essentially using electrolysis, using energy from the sun to actually produce hydrogen. So the concept is as follows. You have the sun, which hits some solar panels, which run your electrolysis system. In an electrolysis system, you actually introduce water into what's called the anode of the electrolyzer. This anode has a catalyst on it, which is what we're studying here. And this catalyst electrochemically oxidizes that water into oxygen and protons. The protons travel through the proton exchange membrane. They meet up at the cathode, which also has catalyst, platinum black in this case, and it actually forms hydrogen. You can then take that hydrogen and you can either store it, pump it, or put it in a vehicle. Now this actually exists. This is a Honda plant that's been around since 2003 here in Torrance, just here in Southern California. And you can see the brand new Honda FCX vehicle that's actually on there. I forgot I had a pointer. You can actually see the Honda FCX pointer on there. Now the whole system's quite interesting. You essentially have your solar panel, your power converter, which powers your electrolyzer, which makes your hydrogen and oxygen. Oxygen you just dump overboard, hydrogen is what you want, and then you actually compress that hydrogen into some hydrogen storage tanks. Now the specifics on this plant are that it takes around 8 kilowatts photovoltaic energy, and it produces around 6,000 liters of hydrogen, and that's per year. So that's basically through a year, and it does this at 5,000 psi. Now what this could get you actually is this could get you this Honda CFX vehicle that could run around 220 miles on a charge, and it could do around 8,000 miles a year. So you can start to understand, oh, this technology is viable. It could actually be something that we could put in our home and something that we could use. Now, my research is all based on trying to lower the power of this 8 kilowatt photovoltaic array. If I could reduce that power to half, I'd be very happy. If I could just reduce it by 30%, it's something that could actually go on the home of a house, and you could actually generate your hydrogen while you're at work, and when you're at home, you can refuel your car. Remember, the whole idea here is to identify an energy carrier, produce that energy carrier, remember this being hydrogen, and use that to actually do something like, for instance, transport us in an electric vehicle. So, when we first started this research, we did a little bit of literature background searching, and we found out that ruthenium oxide was the best material for oxygen evolution. And we said, very good, let's find a technique where we can make a high surface area of ruthenium oxide. Now, there were some drawbacks with using ruthenium oxide, namely the ruthenium oxide is just not stable at all. But we said, okay, we got to start somewhere, let's do this ruthenium oxide. So we went and we developed a process called, it's based on a sol gel process, and it's called a high temperature supercritical extraction, which gives you a real high surface area of your ruthenium oxide. And we went ahead and we made it, and I was jumping for joy, because our standard, this is a plot of cell voltage as a function of the applied current density, and this is what you typically would see when you're looking at electrolysis systems. The lower this curve goes, the better off, the more efficient your electrolysis system's working. But essentially, what you see here is we have commercial ruthenium oxide, which, what I said, was one of the best materials. And then we have this material that we made that was already better. And this was on the first try. We were very excited. One problem is that material only lasted about 2 hours. So 2 hours of testing, it wouldn't work anymore. And we said, oh my gosh. So we looked at different techniques of how to stabilize this material. And one of them was, let's go ahead and heat treat it. So we heat treated it at different temperatures, one at 500 degrees C, one at 700 degrees C. And we noticed one thing, that it was a lot more stable, but the performance was getting worse and worse and worse. And then we sat there and we scratched our heads. We said, oh my gosh, we made this good material, but we actually destroyed it when we heat treated it. So we looked at some XRD patterns of the material, and you can see here, here's commercial ruthenium oxide, here's our as-prepared HTSC material, here's our heat-treated 700 degrees C material. We also went all the way to 1100 degrees C, just to see what this material did. One of the first things that we noticed that blew us away was that our main material was mainly ruthenium metal. Remember, we were trying to make a ruthenium oxide because we knew ruthenium metal wasn't a very good oxygen evolution catalyst. This further perplexed us, and we were saying, my gosh, here we have this metal that we know is not good, but yet it's doing better than even the best stuff that was known. In heat treating, and we did this in air, so this isn't a surprise, we could actually see that we were converting our ruthenium metal, and that peak is getting smaller, and the ruthenium oxide peak is getting bigger. So we were saying, hey, how is this? We're making ruthenium oxide, but yet the material is working less and less and less. Well, what we finally figured out is that we had a non-stoichiometric phase of this ruthenium oxide. And this non-stoichiometric phase is what was making our performance so well. And so we came with this idea. If we could stabilize this non-stoichiometric phase of the ruthenium oxide, we could really get some good results. So we went ahead and we devised 3 different techniques of making this catalyst. One, which was the sol gel, which I presented a second ago. The second was a ball milling technique, where you just take the materials, you use high energy ball milling, and you try to make an alloy out of it. And second was this thermal processing technique that we developed. The reaction that we were trying to get was the metal plus ruthenium oxide, and it would give you this non-stoichiometric ruthenium oxide. And we didn't want to destroy the ruthenium oxide too much. We said 5%, 10%, that's all we want as far as non-stoichiometric goes. We did all these tests. We developed a lot of materials, and we found out that the sol gel process wasn't working out very good. It was hard to incorporate that other metal M. These 2 metals that we were looking at primarily were lead and iridium. Ball milling also didn't work very well. We would end up with alloys, but we wouldn't end up with catalysts that worked very well, and you're going to see that data in a second. Thermal processing, on the other hand, worked out really well. Now, one of the biggest problems whenever you're doing catalysis, or at least electrochemistry, is you want to maintain a high surface area. And as you know, as soon as you introduce something with some heat, sometimes you could get some creep, you could get some coarsening, you could get your powders to basically agglomerate. So we wanted to make sure that we were doing everything correct. So here's ruthenium oxide, this is SEM, 50K and 100K ruthenium oxide. Here's your iridium black, these are our 2 starting materials. And here's the heat-treated iridium, what we're calling an iridium-doped ruthenium oxide. And you can't really tell much from these SEM view graphs other than just looking at them and saying, okay, the morphology is about the same. We really can't talk too much about particle size and whatnot, but we could say they look similar. It doesn't look like anything is getting too different than the base material. So we were very happy with that, and we went ahead and did the next step, which to try to characterize a little more. Now remember, the reaction that we were trying to run was we were trying to get this iridium or this lead and mix it with the ruthenium oxide and get this non-stoichiometric ruthenium oxide. Well, the trouble with iridium was that all the peaks of iridium and all the peaks of ruthenium oxide overlap. So we couldn't tell if we were turning iridium black into iridium oxide, and these are for 3 different concentrations, 5%, 12%, and 40%. The one thing that we did notice, if you look at it around the 47.5, 2 theta degree, is you can see in the iridium black material, you get a little bump. This is kind of one of the secondary reflections of this material, but that bump is gone at 5%, it's gone at 12%, and it's still somewhat there at 40%, which had a lot of iridium black to begin with.